Today we're going to finish section 3.5, which is multiplication and division algorithms, and then today we're also going to look at mental estimation in this section for multiplication and division. And we had gone through a series of, well, we went through some properties of exponents. We went through multiplication algorithms, some different ones of these. And then we had two division algorithms, the repeated subtraction plus our standard algorithm. And we're going to take a look at some application problems, word problems related to these ideas. You might also sort of be asking yourself, I know every now and then people want to know, like, what grade level are we looking at? My son actually brought home stuff that looked really very similar to this. He's in 4th grade just last week. So this material might be hitting about 3rd to 4th grade-ish, depending. So I still feel like that at some level there's some things that he's doing that are review stuff from last year, but we're approximately there. All right, so Juan saved $5,340 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much money did he save per month during the last 2 years? So tell me what kinds of things you see as needing to be done to solve this problem. We've done problem solving stuff in this class, right? What would you need to do in order to solve this problem? Maybe not in a specific order, but just some things. Okay, we might use an equation.
Figure out how much money he saved in the first year.
Okay, so you might want to find out how much money he saved in the first year. If I knew that, what would I do next? What was that? First we would need to subtract it from the amount he saved total, and then we would maybe divide by 2. But if we divided by 2, what would that actually give us? The amount he saved in a year, and what it actually asked for? Per month. So maybe instead of dividing by 2, we might want to divide by 24. Or maybe we would divide by 2 and then divide by 12. We could do that too, just depending on our perception. Okay, so there's, one of the reasons I asked you to do this is there's a lot of steps here, right? And there's a lot going on. I think that Savannah has a good idea, though, for us to start with, which is to figure out how much money he actually saved the first year. So how would I find out how much money he saved in the first year? I would need to do 95 times 12. Okay, so my first step is to do, let's use black, 95 times 12. So I'm going to try and use, as we go through it, some of the different strategies for multiplication and division that we have learned. And it's up to you how you do the problems if you're not told how to do them in your homework and so forth. But I just want to remind you, since it's been now a whole weekend, since we've looked at any of these strategies, how some of them work. So let me take a look at this one, and I'll do this one with you with what's called partial products, which means that we did 90 and 5, and we had a box, and we did 10 and 2 for 12. Okay? So remember the row and the column. What's 90 times 10? 900. And then what's 5 times 10? 50. 90 times 2? 180. And then 5 times 2? 10. And then what would I do with all of those numbers inside? I would need to add them up. So if I added 900 plus 180 plus 50 plus 10, what would I get? 1,140. And what did we just find? Yeah, this was saved in year 1. Just to help keep us track where we're actually at in the problem. He saved $1,140 in year 1. What would he need to do or what would we need to do for the next part of our problem? Okay, so our next part of the problem would be to take the amount he saved total, what was it, 5,340, and subtract 1,140. It's actually a really nice subtraction because there's no regrouping, right? What would I get if I subtract those? 4,200. Yeah, we could do that divided by 2 and then that divided by 12, or we could divide it by 24. In some regards, dividing by 24 would be faster, but maybe not easier, right? Because dividing by 24 is multiplication and division tables that we probably don't have facts memorized for. So sometimes the fastest is not always the best way to go. So let's do it as you suggested, which was to divide by 2 and then to divide by 12. So if I divide by 2, what do I get? Yeah, 2100. And then I can do 2100 divided by 12. So let's just use our standard algorithm with this one this time. So with the 12s tables, most kids know up to 12 tables at this point. I find that to be actually a little bit interesting. I was having a conversation with my children the other day. I didn't learn 12s tables. I mean, like, I know them more or less, but that's not what we did. We only learned up to our 10s. Absolutely did not learn 11s as 12s. That just wasn't a thing. So I don't know why the push to do that exactly has changed, but it has. So how many times does 12 go into 21? One time. And then if I subtract 21 minus 12, what do I get? 9. And then we'll bring a 0 down, right? So you have 90. So how many times does 12 go into 90? 7. I'm cheating too. Like I told you, I don't know my 12s table. 7. 7 looks good. What's 7 times 12? 84 is right. And if I subtract, I get 6. And then bringing my 0 down one more time, I've got 12 goes into 60 how many times? 5. And that's it, exactly 60. So remainder of 0. So this is my final answer, at least the numerical portion. But what does it mean? Yeah. He saved $175 per month. So could we have set this up with an equation? Julia suggested this, and yeah, we could have. That would have been another way to do the problem. So there's not always one way to do things right or wrong kind of deal. I mean, this is problem solving. So this one is a fairly nice way of doing it with some of the basic operations that we've been doing in this section. So we'll go with this one. All right, let's try another one. Dan apparently collects pennies because he has quite a few of them. He has 4,520 pennies. Actually, you know, when I was a kid, my grandfather did have us do pennies, and we did them in books, and we took the shiny ones, and we kept them in a penny book. I don't know if you guys ever did things like that, but it was a big deal with him. 4,520 pennies for Dan, and he put them in 3 boxes, and he says there are 3 times as many pennies in the first box as in the third box, and there are twice as many in the second box as the first. And the question is, how much money does he have in each box? So, what might you start by doing on this problem? Well, that's what we're going to end up doing, is figuring out how many are in each box. Okay, so we might need to use variables on this one, right? It seems like a reasonable assumption that we might have to, or we might want to try and assign variables to this particular problem. I am a visual person. I've told you that before. So I might actually start by drawing 3 boxes. That's probably what I would do. And then I would assign the variables like Savannah said. So if I were to draw 3 boxes, and I can label them box 1, 2, and 3. And then I think, Savannah, you were already telling me how I would maybe put my variables in my boxes. What did you have an idea of?
The first one would be 3x.
Okay.
And then the third one would be x.
Okay, so there's a relationship stated between boxes 3 and 1. It says that there are 3 times as many pennies in box 1 as box 3. So that's why she set up the relationship with x and 3x. That makes sense to everyone. Okay, now given those 2 pieces of information, what would be in box 2? 6x. How come? Yeah, there's twice as many as in box 1. So if box 1 has 3x, box 2 is going to have 6x. Okay, so now I've got a picture with 3 boxes and I've got x's everywhere. How am I going to use all this information next? Okay, so if I were to take all my pennies, which are represented by the 3x, the 6x, and the x, and I were to add them all together, right, like dump them all out on the floor, heaven forbid, what would happen besides making a big mess? Yeah, it should equal the 4,520 pennies, right? Unless I lose one. So we'll assume we don't lose any. And I have all the pennies when I've dumped them all together on the floor. Okay, so here's an equation on this one. It seemed like a natural way to start this problem. What would I do next? Okay, so if I add all the x's together, what do I get? 10x equals 4520. And then what? Divide by 10, you bet. So what would x equal? 452, right? Now, we solved the equation we created, but we need to make sure we answer the questions we were actually asked. What is the 452 so far? What piece of information have we found? Yeah, we found out how many are in box 3, right? So there are 452 in box 3. Now what? If I multiplied that by 3, so 453 times 3. So let me show you a lattice algorithm for this one because we haven't done but one of those.
452.
Oh, 52. Thank you. Let's make sure we do get the right ones. Appreciate that. Okay. So if you'll remember, the lattice algorithm works like this. Because I have a 3-digit by 1-digit number, I would have 3 boxes by 1. I would have the numbers 4, 5, 2 along the top, and the number 3 on the right. Okay. And then I would split my boxes up, and each box would correspond to the row and column it's on. So the first one is 4 times 3, which would be 12. You were looking at the ending one. That's okay. In the middle, I have 5 times 3, which would be 15. And the ending one is the 6 that you saw before. That's all right. Okay, and then we extend our diagonals and add along them. So I have a 6 in the bottom right-hand corner. Moving to the left, I have a 5. Moving further to the left, I have 3, 2 plus 1, and then I have a 1 over here, 1356. So I have 1356 pennies in box 1. And then what will I do? I need to multiply that by 2. So 1356 times 2. And let's do this one with the standard algorithm. So 6 times 2 would be 12. 5 times 2, 10, and then I have to add a 1 to make 11. 3 times 2 would be 6 plus 1 is 7. And then 2 times 1 would be 2. So there's 2712 pennies in box 2. Have I answered the question? I'm getting really close, but not quite yet. What's missing? It wants to know how much money is in each box. And while you might be able to argue with me that you've given me the number of pennies in the box, that's not really how we talk about money, right? I mean, like, even if I have, 10 cents, I don't usually say I have 10 pennies, which is sort of how this is being described, right? We usually describe it in terms of dollars, especially with the numbers as big as they are. So let's actually write out to the side over here our answers. How much money is in box 1? $4.52. Whoa, that was box 3. That's what I meant to do. I'm sorry. I'll go back. We'll do box 1 first. What was box 1 again? $13.56. Thanks. Box 2, that's my biggest box. $27.12. And box 3, that's $4.52. All right, You good with that? All right, I want to show you an interesting question. Students do this all the time. You guys maybe have even done this before, where you go up to your professor or your teacher, elementary school or high school, and you're like, look what I found. Does this actually work? Or I tried this other method and I got the right answer. Is this okay? And so this is an example like that, where a student has observed something and they want to know if it actually works. So a student observes that 39 plus 41 is 40 plus 40. That's true, right? It is. And they want to know if 39 times 41 is 40 times 40. Okay, so you're immediately shaking your head no, Alicia. What do you notice right away? Or what makes you so certain to say no, it's not going to work?
Because it's not a trade-off like it was on the first one.
Okay, I think that's a good description, right? Like, so the first one was an addition problem, and we were trading off by using addition and subtraction, right? The second problem is a multiplication problem. So the idea of trading off with addition and subtraction in the middle of a multiplication problem probably is not going to work. It doesn't seem like an equitable operation, right? Like if we traded off by multiplying and dividing, that might work. But it seems like from the middle of the multiplication and division problem, probably not going to be able to add and subtract to figure out whether or not this is going to simplify. How could we show the student very specifically that this doesn't work on this problem? You could multiply it out, right? So I could multiply out the left, I could multiply out the right. If you wanted to do it quicker, you could actually look at the multiplication of the ones digits, just that. What happens when I multiply 40 times 40? Just right here. I get a 0. Is that going to happen with the other two digits? Not possible, because they don't have any zeros in them, right? You can't multiply 39 and 41 and end up with a 0 here. It's not possible. So there's no way that these are equal. So showing them in some fashion, we can talk about the trading off, and that might actually give them some sort of sense of why it's not working, right? But to show them that it just flat out doesn't work, very specifically, we can show them an example using the one they gave, right, of why it doesn't work. If you wanted to shortcut the example and just show them it immediately, the ones digit doesn't work. That's also an appropriate response. But any of those would be a good way to respond to the fact that, yes, it's not going to work. But then we have another student who notices another thing. So another student notices that when you multiply them, like we were expecting, and you subtract 1 from the right-hand side, it actually works. It's not a question of does it. It does work. And then he also finds that if you do 49 times 51 and make that 50 times 50 minus 1, it also works. And he wants to know if the pattern continues. And if it does, what does the relation have to be between the first two values in the equation that we're working with? They look like they're, I think you would mean 2 then.
Yeah.
2 digits apart. Yeah, it looks like 39 and 41 are 2 digits apart, and 49 and 51 are 2 digits apart, right? So that part of the pattern seems quite reasonable that might be what's happening. One way to check it would be to just randomly check a couple of numbers that are 2 digits apart and see if that works. So let's try one, and you can even grab your calculators for what we're working on this problem if you'd like. Give an example. Give me 2 two-digit numbers that are 2 apart. What's that? All right, 27 and 29. And the question is, when I take 27 and 29, will I get the same thing if I do 28 times 28 and minus 1? So double check it and let's see if it works. This is a very random guess.
They're both the next odd number apart. 39 and 41. 49 and 51.
Yes, they're 2 apart, right?
But then we just do 2 apart with this one.
Yes. We're trying to see if the pattern continues.
Oh, okay.
Yes. Yes, we're trying to see if the pattern continues. The other thing that you might notice on these is that they're actually 2 apart surrounding a single digit of 0. Like, is that necessary, or is that just sort of it worked out on these and it maybe doesn't work out on the other ones because that 0 doesn't matter or not? So trying this one actually can give us a good sense of whether or not that 0 matters too. So what is 27 times 29? 780? 3. 3. Thank you. And then what happens when you do 28 times 28 minus 1? Is it the same? Yeah, it is. So it seems reasonable for us that we would conclude that this probably works, right? We tried a very random example that didn't happen to be separated across a digit of 0, so it wasn't like 19 and 21 or 29 and 31, separating across the tens or like a tens power. It's not like that, or tens place. So it seems like a reasonable thing that would work. So let's actually take a look at what's happening in terms of just a little bit of algebra so that you can see why it would work. And maybe how you would think about trying to prove to yourself that your guess actually ends up being a little bit stronger than just like I randomly guessed and it works. And yeah, it works on everything. It's not a very good claim. I mean, that's not a good statement to make because it doesn't always work that way. So let's say, for instance, we had two numbers we supposed that were 2 digits apart. We could represent them like this: x and x plus 2. Make sense to everyone? What's the number in between them then? It is x plus 1. So we're trying to say that if I then took x plus 1 times x plus 1 and subtracted the number 1, we're claiming that this is equal. Okay, so this piece right here is a big question mark. We don't really know it's equal. We're trying to see if it's equal. So let's see what happens when I do x times x plus 2. What do I get on the left-hand side? We haven't done a lot of algebra in this class, but what would I get if I distribute through here? Good, x squared plus 2x. On this one, you have to remember on the right-hand side to distribute. So this x has to distribute to the x and the x 1. So this would be x squared plus x. And then it also has to distribute through when the 1 goes to each of them, which would be another x and plus 1. And I've still got that minus 1 on the end. So if I clean up the right-hand side, what am I going to have? X squared plus 2x. The very same thing I already had on the left-hand side. It works. And that's actually a justification, at least to you, probably not to show your kid in the class, but to you, that it really does work all the time. Because it doesn't get any more general than calling something x, right? Random was deciding we were going to use 27 and 29. General is deciding we're going to use x and x plus 2. Okay, so let's answer some of the questions asked. They say, what does the relationship have to be between the first two values? So what would the relationship have to be in order for this to work, according to the information we've sort of played around with here? Yeah, the first two numbers must differ by 2. And if you wanted to try an example, I'll just give you an example real quick that doesn't work because it fails that right there. Let's say, for instance, that you had 25 times 35. Well, halfway in between 25 and 35 would be 30, right? Just like the other ones. And the question is, if I do 30 times 30 and I minus 1, will that be the same thing? And it's not going to be there. We don't even have to multiply it out, hopefully, to see, because 5 times 5 is going to give you 25. And this 0 and 0 is going to give you a 0. And then you subtract a 1, you're going to get a 9. The 1's digits immediately are going to be off. But if you wanted to very, concretely show it to a child, what happens when you do 25 times 35? What do you get? Somebody grab a calculator. $875. And then 30 times 30 would be 900. So this would be $899. Yeah, not going to work, right? Not going to work. So the fact that they are separated by 2 digits, right? Or 2 digits apart, their difference is 2, actually is very crucial to this working. Okay, I want to show you some mental math stuff. Are you ready? I like mental math. Anytime I can shortcut something in my brain and not have to write something down, that's like bonus in my book. So let's take a look at a few mental math strategies. The first one is called Frontend Multiplying, okay? So Frontend Multiplying works really well when you have small digits. If you had like a 4-digit number times 5. Like this didn't just say 46 times 5, it said 4,652 times 5. Front-end multiplication would not be a good choice, okay? Because what front-end multiplication has you do is it breaks it apart into 40 and into 6 and has you multiply each value and then re-add them together. Whoops, it's supposed to be 5. What is 40 times 5? 200. What is 6 times 5? 30. And if I were to add them together, I can do 230. That's few enough steps you can do it in your head without writing it down. At least a lot of people could. Maybe you can't, and that's okay. But that's the idea. That makes sense. If I asked you to do 4,625 times 5, and you decided that a good mental math strategy would be to multiply 4,000 times 5, 600 times 5, 20 times 5, and 5 times 5, and then take all 4 of those numbers and add them together, we're going to have a talk, because you're doing probably better than I can, because I don't think I can keep track of that much stuff in my head at one time. And that's the goal, right? It's supposed to be mentally. So this method has some restrictions. It doesn't just work forever. It really works in some smaller scenarios. Everybody good with that? So you're just breaking it apart and you're doing the individual pieces of multiplication, the front end, and then you're adding together at the back end. We've done compatible numbers before with addition. Compatible numbers with addition were 2 numbers that basically added together to something that was like 10 or 100. Those were compatible. Very similar for compatible numbers with multiplication. We'd like to take numbers that multiply together to give us something that's like a 1-digit number. For example, 30. 30 is fantastic because really it's a 3 and a 0. And zeros are great to multiply with, right? It really acts a lot like a 1-digit number instead of a 2-digit number. So taking a look at the numbers that are given here, 4, 8, 5, 5, 2. Are there any 2 numbers in whatever order you have that you could multiply that would be giving you a really nice something with a 0 in the ones place? What do you have? 4 times 5. Okay, so if I did 4 times 5, what do I get? 20. That's a great number. Somebody give me another pair I could use. 5 times 2. That would give me a 10. What if I had done 5 times 8? Would that have been a good one? Actually, it would have worked really well on this one too. And I just have my 8 at the end on this one because I haven't used it yet. What is 20 times 10? 200. And then 200 times 8. 1,600. There are a couple of bad choices. What would not be good choices to multiply together first? 4 times 8 would be terrible. I mean, it really would. It wouldn't get much worse than 4 times 8. You know what I mean? Yeah, not good. Anything else that would not be super helpful? 2 times 8, not helpful. Honestly, 2 times 4 is not that helpful either. It's not terrible, but I don't really need another 8 in there, right? I mean, like, give me something that's going to get rid of something bigger, you know, at the same time. So this is compatible numbers. You're looking for numbers that multiply together and end up giving you a 0 in the ones place, really. The next strategy is possibly something you've never thought of before, and it's a really cool strategy. And by the time I get to the test, I usually have at least 3/4 of the class that does not remember this strategy at all. I don't know why. I don't always ask the question about it, but every time I do, 3/4 of the class doesn't know what I'm talking about when I get here, okay? Thinking money. All right, so there are some coins that we have that are certain values that are convenient to use. For example, 1, the number 1, works very well to be thinking of as a penny, right? Can you think of another number we have that it's representative by money very well? A 5? What would a 5 be? It would be a nickel. Is that right, or EL? I think it's EL. What other numbers do we have for coins? A 10 would be a dime. I need one more coin. Yeah, a 25 would be a quarter. So clearly, I'm not always multiplying by 1, 5, 10, or 25. But sometimes I do, like in this problem, right? So if I happen to be multiplying by one of these numbers, money is often a nice strategy. So this 5 right here could be thought of as taking 46 nickels, because 5 is worth what is what a nickel is worth. Okay, so I mean, like 46 nickels. If I had 46 nickels, that is not the easiest way to multiply something. But it'd be a lot easier instead to talk about having 23 dimes. How are 46 nickels related to 23 dimes? Why does that work? Yeah, 2 nickels is equal to 1 dime. So if I took my 46 nickels and I traded them in 2 at a time, each of them times I traded them in for a dime, I'd have half as many dimes when I'm done. But 23 dimes is easy multiplication. Because what happens when I try to do 23 dimes? I get something with a 0 in the ones place, right? What is 23 times 10? It's 230. I'm trading in my uneasy to work with nickels for easy to work with dimes. That's what I'm really doing. I'm making my dimes the focus instead. Okay, the next problem is the similar one, but what it's being multiplied by is what? It's 25, but 25 could represent what? Quarters. Now imagine that you had 44 quarters and you didn't need to go to the laundromat or the car wash, so you didn't need all the quarters, right? You guys don't even know what I'm talking about because you've never had to do that, right? I don't even think you have to do it on campus, do you? They don't even make you pay for your laundry on campus. Yeah. It's a thing of the past. All right, you got 44 quarters and you don't want to carry that many quarters in your pocket. How about that? I know that's true. You don't want to carry 44 quarters in your pocket. What could you do to make your pocket lighter? You could make that $11, right? Because 4 quarters is $1. Now, I didn't write that down on the previous slide, but the reality is that in this scenario, if I'm looking at coins, 100 would represent $1, right? 100 pennies would be the same thing as $1. So when I multiply by $11, that's the equivalent of having 11 times 100, which would be 1,100. So 44 times 25 is actually 1,100, because I can think about it like money. Okay, let's do some with division. I think the last 4 are all division, looks like, yeah. This is called breaking up the dividend. So breaking up the dividend looks like this. We're going to take the 6318. And we're going to notice that 63 and 18 individually are in the list of multiples of 9. And 9 is what I'm dividing by. Does everybody see that? Okay. That's what makes this a good method to use here, is because I can break the 63 up as 6,300. And I can make that 18 at the end. And then each of the individual values that don't involve the zeros divide evenly and nicely by 9. So what is 63 divided by 9? 7, yeah. But it's 6,300, so this is 700. What is the 18 over here divided by 2, or by 9? 2, yeah. I'm jumping the gun on you, sorry. All right, so I'm just dividing each one of them individually by 9. This one divided by 9 was 700. This one divided by 9 is 2. So that gives me a total of 702. So am I always going to have numbers that are going to evenly divide by the divisor? Well, no, of course not. But if I do, this is a strategy that works really nicely. Now, sometimes I don't have ones that work out quite that nice, but they're like almost that nice. This would be an example of one. I can actually see the 25 at the end working out well for me, right? Yeah, I mean, 5 divides 25 very nicely. 5 does not divide 4 very nicely, but it does divide 400 very nicely. So if I think of the 400 and the 40 part of it, what is 40 divided by 5? That's 8 for 80. And then 25 divided by 5 is 5. And 80 and 5 would be 85. Okay, the very first strategy in mental math that we did today was called Frontend Multiplying. And we took each of the first numbers, you know, all the way down the numbers basically, and we multiplied by the value, the second value. In our case, it was 5. There's also something called Frontend Estimation. Frontend Estimation means that I'm not going to multiply every single value by 4. That'd be Frontend Multiplying, like finding an exact number. I'm not going to do 300 times 4, 80 times 4, and 6 times 4. It's not what I'm going to do. We're just going to do the first two, because that's about the extent that mental math makes sense to do, you know, in your head for this. I mean, that's the deal. So it will be an estimation, but what we're going to do is we're going to do 300 times 4. We're going to do 80 times 4, and then we're going to add them up. 3 steps. That's it. So what is 300 times 4? 1200. And 80 times 4. 32 with the 0, so 320. And then if I add them together, what do I get? 1520. Now, is this exactly my answer? No, because I didn't do the third step, if you will, and actually do 6 times 4. Okay, it's an estimation. If the number had been bigger, we would do the same thing. Let's say that the number had been 324,692 times 8. And it's a big number. All we would do is we would take the 300,000 times 8, and we would take the 20,000 times 8, and then we'd add them up. That's front-end estimation. 2 steps of multiplication, 1 step of addition. Okay, no matter how big the numbers are. Estimation. And then I have a front-end estimation, compatible numbers with division. Compatible numbers with division. So we mentioned earlier it's often nice to sort of break the numbers apart. For this one, we're using estimation, which means that we don't have to break them apart into the exact values, but just values that are close and easy to work with. So 4,132 divided by 4 would be awfully close to what other number divided by 4 that's so much easier to divide? What's that? 4,032 would be not too bad. We could do that. It's estimation, so we could do it even easier if you want. If you want to do, you could do 4,000 divided by 4. That one's easier even to estimate, right? And either of these answers would be great, and they both divide very nicely, right? If I did 4,032 and I broke it apart here, right, I could do what I did before with my 4,000 plus 32 divided by 4. So this would be 1,000 plus 8 for 108, 1,008. Or if I did 4,000 divided by 4, I could simply get 1,000. 1,000 and 1,008 are fairly close numbers already, right? Yeah. And there was estimates of what I had already before. All right, any questions on this one? All right, so here's what we're gonna do. We only have like 3 minutes left, which means it's worthless to put you in groups really for 3 minutes. We'll do this group work next time. So you don't have to do any homework on this tonight. If you want to, you can, but it won't be due until you come back after spring break, or not spring break, that would be a really long time. Yeah. Fall break, we'll get the right season in there. So this assignment will be due on Monday after fall break. But remember, the Success Center is not open over fall break. So if you're someone who likes to go and get work checked or double checking there, please make sure you're going and getting help tonight, tomorrow night before the Success Center shuts down for the break, okay?